The solar system. In this lesson, we'll explore the science and engineering practices of developing and using models, using mathematics and computational thinking, and constructing explanations and designing solutions. Our cross-cutting concepts include scale, proportion, and quantity, as well as systems and system models. The formation of the solar system. Our solar system is part of a galaxy known as the Milky Way. It is about 5,000 million years old. Scientists believe that it was formed over a very long period from a nebula, an enormous swirling cloud of gas and dust found in galaxies. Scientists believe that something, maybe an explosion of a nearby dying star, which is called a supernova, caused the dust particles to begin to clump together and form a dense spinning cloud. As more dust accumulated in the core of the cloud, its gravitational pull increased. This caused even more dust to be sucked in until eventually the cloud collapsed in on itself. This collapse caused nebula to spin faster until it flattened into a core surrounded by a disk of gas and dust. Temperatures increased dramatically, prompting nuclear reactions to start taking place in the core and resulting in the birth of the sun. The material in the disk formed the planets and asteroids of the solar system. The solar system is made up of various objects orbiting the sun, including 8 planets, at least 5 dwarf planets, satellites or moons orbiting the planets, asteroids, and comets. The sun is the star at the center of the solar system and was born about 4.6 billion years ago. It is approximately 109 times the size of the Earth's diameter and 150 million kilometers away from us. The sun's mass accounts for more than 99% of the total mass of the solar system. The sun's energy comes from nuclear fusion. Most of this energy is emitted as electromagnetic radiation in the form of heat and light. The sun has enough nuclear fuel to last another 5 billion years. Planets, dwarf planets, and moons. Planets are objects that orbit a star. The planets in the solar system are, in order of distance from the sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. I've shared with you my mnemonic device. My very earnest mother just saved us 9 pennies, but we know that Pluto has now been classified as a dwarf planet. Maybe another mnemonic device is my very easy method just speeds up naming. And that'll help you remember the planets in order. Again, Pluto is no longer considered a planet, having been reclassified as a dwarf planet in 2006. According to the International Astronomical Union, 1. A planet is a celestial body that A. is in orbit around the sun, and B. has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium, nearly round shape, and C. has cleared the neighborhood around its orbit. And that right there is kind of the sticky part, in that there's still objects kind of in the orbit of Pluto. Number 2, a dwarf planet is a celestial body that A. is in orbit around the sun, B. has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium, nearly round shape, And C has not cleared the neighborhood around its orbit. And D is not a satellite. Number 3, all other objects except satellites orbiting the sun shall be referred to collectively as smaller system bodies. So just some general information there. Dwarf planets also orbit stars, but they do not have enough gravity to be considered a planet. Pluto has been classified as a dwarf planet since 2006, which we already discussed. Most planets are orbited by their own natural satellites, and these are called moons. Asteroids, meteoroids, and comets. Asteroids are large rocks that normally orbit the sun. Sometimes asteroids collide, causing debris, meteoroids, that can then collide with the Earth. The path of a meteoroid as it burns up in the Earth's atmosphere is called a meteor and can be seen as a streak of light in the night sky. If a meteoroid doesn't burn up completely, it can hit the Earth, and it is then known as a meteorite. A comet is an icy body surrounded by a cloudy atmosphere with a highly elliptical orbit around the sun, meaning that at certain times it's closer to the sun, and then at other times in its orbit it's a long ways away from the sun. Comets release gas or dust tails as they travel, which may be seen from Earth. This image shows the asteroid 243 Ida. The image was taken by the probe Galileo on the 28th of August, 1993. Ida has an average diameter of around 31 kilometers. It does not have a regular shape. Ida has a satellite that orbits it called Dactyl that we can see in this image. Dactyl has a diameter of around 1.4 kilometers. Both Ida and Dactyl are found in the asteroid belt located between the orbits of Mars and Jupiter. It is thought that more than 99.8% of the 30,000 meteorites found on Earth to date originated in the asteroid belt. So why do planets orbit the sun? The planets of our solar system travel in almost circular orbits around the sun because of the force of gravity. The strength of the gravitational attraction to an object depends on the object's mass. Small, everyday objects, such as a relatively tiny mass, that we do not notice the gravitation attraction to them. With larger objects, such as planets, moons, and stars, the gravitational attraction is much more noticeable. The orbits of the planets around the sun are elliptical rather than perfectly circular. The pull of the sun's gravity causes the planets to speed up when they move towards the sun and slow down when they move away from it. The changing speeds of the planets as they orbit the sun make it very difficult for the orbits to form a perfect circle. It's important to recognize, though, as we are traveling around the sun, the point at which we are closer to the sun is pretty minimal comparative to the point where we are farther away. It's also important to recognize that the point in our orbit where we are closest to the sun is not our summer, it's actually the northern hemisphere's winter. Newton's canon. What is an orbit? In 1728, Sir Isaac Newton published details of a thought experiment which hypothesized how objects become trapped in orbit by the Earth's gravity. Newton imagined a mountain so tall that the mountain peak was above the Earth's atmosphere. Newton then imagined a cannon on top of the mountain. Newton knew that when the cannon was fired, the cannonball would travel a certain distance before hitting the Earth. If more gunpowder was used, the cannonball would travel even faster and over a greater distance before hitting the Earth. If sufficient gunpowder was used, the ball would travel at the right speed to miss the Earth and be in orbit. This happens when the ball falls at the same rate as the Earth curves away. Newton believed that if a lot more gunpowder was used, the cannonball would travel so fast that it could escape Earth's gravity and never return. He realized that all objects in orbit are accelerating toward the object they are orbiting. Like the cannonball, the moon is constantly falling toward the Earth without actually reaching it. Orbit height and speed. Imagine that the mountain in Newton's thought experiment was lower. If the same amount of gunpowder was used, would a ball shot from the lower mountain travel the same distance as from the high mountain? No, more gunpowder would be needed to make the ball travel the same distance. Therefore, more gunpowder would be needed to make the ball go into orbit, and the ball would travel faster. This means that if an object orbits the Earth at a lower altitude, it needs to travel faster to stay in orbit. Planetary motion. The orbits of planets around the Sun, as well as the orbits of satellites around planets, can be described using Kepler's 3 laws of planetary motion. Kepler's first law tells us that planets move in slightly elliptical orbits, with the Sun at one focus of the orbit. An ellipse is a squashed circle with 2 foci. The sum of the distances from a point on an ellipse to each focus is the same for any point on the ellipse. Ellipses. The shape of an ellipse can be described by its eccentricity, E, which depends on the distance between the foci, and F, and the length of the major axis, D. E equals F divided by D. The table shows the eccentricities of the orbits of the planets in the solar system. An eccentricity of 0 is a circle. So the information in the table shows that the orbits of planets are almost circular. Kepler's second law. Kepler's second law describes the speed of an orbiting body. It states that a planet sweeps out equal areas in equal amounts of time. This means that planets move fastest when they are nearest the Sun. Equal areas, equal time. Kepler's third law refers to the time it takes for a planet to make one complete circuit. This is known as the time period of the orbit. Kepler's third law states that the time period of an orbit is proportional to the cube of its semi-major axis, r. Kepler derived this law from the experimental data in a 1605 experiment. There was no theory available at the time to account for it. Sir Isaac Newton later derived a full mathematical expression using his theory of universal gravitation. As a side note, the semi-major axis is half the major axis. That is, half the length of the longest axis of the orbit. Newton's law of gravitation. Newton's law of gravitation states that the force between objects with masses m and m is where g is the gravitational constant and r is the distance between the objects. Planets move in almost circular orbits, so the resultant force on the planet with mass m is approximately equal to the centrifugal force. Combining these two equations and rearranging gives v squared equals gm divided by r. You should note that the speed of a planet in orbit does not depend on the mass of the object. Only the mass of the sun and the distance between the planet and the sun. Orbital period. The period of a planet's orbit, t, is the time taken for a complete orbit. Knowing that v squared equals gm divided by r, we can eliminate v to give an expression relating t, r, and m. T squared equals 4 pi to the second, r to the second, divided by v to the second. Or t squared equals 4 pi to the second, r to the second, times r divided by gm. This is the full mathematical expression of Kepler's third law. Factors affecting near-circular orbits. The force required to keep a planet in circular or almost circular motion depends on mass, radius, and speed. But the gravitational force that a star actually provides only depends on mass and radius. This means that for any specific radius, a planet must move at one specific speed to stay in a stable orbit. If a planet orbits a star at an increasing speed, the force between them does not increase, so it moves out of that orbit. Circular motion under gravity. Circular motion under gravity is subtly different from other types of circular motion. So let's experiment. We've got an object in orbit. Circular motion under gravity. Let's speed up the planet. Notice what is happening to the radius of orbit. What if we slow it way down? Notice that the speed of the planet is related to the radius of the orbit. There is an inverse relationship. What if we change the mass of the object? The radius and the speed do not change. What if we reduce the mass of the object? Again, nothing changes as far as speed and radius. This activity is designed to demonstrate that for any particular radius, there is only one speed a planet of any mass may move at in order to stay in that orbit. It can also be used to emphasize the fact that the mass of a planet does not affect its speed and radius of orbit. Comets. Most of the planets travel around the sun in near circular orbits. Comets also travel around the sun, but in highly elliptical orbits. The head of the comet is a lump of ice and dust a few kilometers across. The tail only appears when the comet is near the sun. It consists of gas and dust which are released from the comet by the heat of the sun. This animation is based on the orbit of Halley's Comet. Halley's Comet is atypical because it orbits the sun in a clockwise rather than counterclockwise direction. The orbits of comets around the sun are highly elliptical. The speed of a comet increases as it approaches the sun and decreases as it moves away. Comets orbit the sun because of the sun's gravity. As a comet's orbit takes it closer to the sun, the effect of the sun's gravity becomes greater, and the speed of the comet increases. As the comet then moves away from the sun, the effect of the sun's gravity is not as strong, and the speed of the comet decreases. A comet's tail is actually a stream of dust and gas that is blown off the comet by the solar wind of the sun. The tail of a comet is more visible nearer to the sun and always points away from it.